Hello everyone. My name is Zhao, and my partner is Chaohao. And the paper we introduced today is the learning to design circuits. As we know, the analog circuits process continuous signals, which exist in almost all electronics systems and provide important functions of interactions, real-world signals with digital systems. And the analog IC design has a large number of circuit parameters to tune, and in there, which has highly difficult for several reasons. So there are two main problems when we want to tune the circuit. And the first one is the relationship between the parameters and the performance is subtle and uncertain. The designers have few explicit patterns or deterministic rules to follow. And analog circuits, octagon characters, and strong compelled relations among the performance metrics. So a prepared and intelligent trade-off between these metrics require rich design experience and iteration. And the second problem is the simulation of circuits is slow. It's very slow, and especially for complex circuits such as the ADC, DAC, and the PLL. That makes the random search or exhaustive search impractical. So at the present, there are many ways to realize the automation of circuit parameter search process. The first approach is the practical swarm intelligence. This is a very popular approach now. However, this approach is easy to fall into local optima in high dimensional space and also suffers from a low convergence rate. And the second one, the simulated annealing is also utilized, but repeated annealing can be very slow and easy to fall into the local minimum. Although this new algorithm can be used to solve the optimization problem, the purpose is stochastic and the lakes reproducibility. And the third one, the researchers also proposed a model-based simulated basis hybrid massive and utilized bias optimization to search for parameter sets. However, this approach the computational complexity of bias is prohibitive and make the runtime very long. And the machine learning is another permission method to address the above difficulties. But supervised learning requires the large-scale data sets which consumed a long time to generate. And most of analog IPs are proprietary, and this is not available to the public. So this paper introduced the L2DC method, which leverage reinforcement learning to generate circuits data by itself and learning from the data to search for the best parameters. In each iteration, the agents obtain observations from the environment and produce an action. The action is a set of the parameters, and this action to the circuit simulated environment, and then receive a reward as a function of gain, bandwidth, power, error, and so on. The observation contains of DC operating point, AC magnitude, and the phase response, and also translated states obtained from simulator such as H-space and the spectrons, and the reward is defined to optimize the desired finger of matrix, composed of several performance metrics. By maximize the reward, RL agents can optimize the circuit parameter. So this paper think about the problem definition first. The design specification of an analog IC contains hard constraints and optimization targets. For hard constraints, designers only need to meet them with no need for any over optimization. And for the optimization targets, the rule is the larger the better, or the smaller the better. So for the optimization targets, there are also except the thresholds indicate the minimum performance designer need to achieve. And then this paper formalized the problem. They denote the x belong to Rn as the parameter of each component. Y belong to Rm as the spec to be satisfied, include the hard constraints and the source for the optimization targets. And they consume the mapping Rn to Rm as the circuit simulator, which compute the M performance matrix give N parameters. And then they defined a ratio Q for each spec C to measure which extent the circuit satisfy the spec. If the matrix should be larger than the spec C, QCX equal to the QFCX divided by YC. Otherwise, QCX equal to the YC divided by FCX. And then the analog IC optimization can be formalized as a constraint optimization problem. And in these questions, we just need to maximize the sum of the QCX of optimization targets with all of the hard constraints being satisfied. And we can see an overall of R2DC method in this figure. R2DC is able to find the optimized parameters by several epochs of interaction with the simulation environment. Each epoch contains T steps. For each step I, the RL agents take an observation OI from the environment and then output an action AI, and then receive an reward RI. By learning from history, the RL agent is able to optimize the exact cumulative reward. So for the step of the observations, at each step I, the observation OI is separated into global observation and each transistor's observation. And the global observation content high-level feature of simulation result include the DC operating point voltage and the current at each node, AC amplitude, phase response, and one hot vectors encoding the current environment step. And the local observations are the feature of the ICE transistors contains the voltage and gain and the capacitors between the transistors pins and so on. And the initial value of all global observations and the local transistors observations are set to 0. And then go to the action space part. Suppose there are n parameters to be searched. First, the reference learning agent would output a normalized joint action AI as the predict parameter of each component at each step, and then this normalized AI are scaled up to the AI according to the maximum or minimum constraints of each parameter. And this AI contains the width and length of the transistor, capacitance of capacitor, and the resistance of resistor. And then for the reward function, after reinforcement learning agents output circuit parameters AI, the simulation environment F will benchmark on this parameter, generating the simulation result of various performance metrics, and then they gather the matrix together as a scalar score DI, called DI, and they just denote the KIX as the sum of the QC of this hard constraints, and the K2X as the optimization target. Then the DI is defined as the formula as we see. From this formula above, we can see when the hard constraints in these spikes are not satisfied, the DDPG will optimize the hard constraints requirements first, and then optional optimization targets requirements according to the coefficient alpha. If all hard constraints are satisfied, the DDPG will only focus on the optimization targets. And in this formula, we can see that E0 and E1. E0 and E1 are two constants. They are used to make sure the score after hard constraints are satisfied are higher than those before the hard constraints are satisfied.
All right, this is Chaohao presenting. Now we're looking at DDPG agent. DDPG actor forms an encoder and decoder framework, which translates the observations to the actions. As you can see on the bottom of the slide, this function is what we use to actually design the encoder and decoder. The order which we follow to feed the observations of transistors is the order of signal propagation through a certain path from input ports to output ports, because the former components influence later ones. The decoder generates transistor W and L in the same order as well. Now let's look at the experimental results. The first environment is a 3-stage transimpedance amplifier from the final project of Stanford EE214 class. The schematic of the circuit is shown in left. We compared L2DC with random search and grid search aided human expert design proposed by a PhD students in EE214A class as well as MACE, a Bayesian optimization based algorithm for analog circuit optimization. The batch size of MACE is 10, and we use 50 samples for initialization. The comparison results are shown in the table. The DDPG's design can meet all the hard constraints and has slightly higher power but smaller gate area than the human expert design. So it achieves a pretty high score. The power consumption of DDPG, though slightly higher than human design, can satisfy the course specification constraints. The number of simulation of DDPG is 250 fewer than the grid search aided human design, which means it has pretty high sample efficiency for L2DC method. Random search is not able to meet the bandwidth hard constraint because there are 17 transistors, making the environment very complex and making the design space very large. BO is also unable to meet the bandwidth and power hard constraints. The second environment for the experiment is the two-stage transimpedance amplifier. The schematic is shown on the left. We run DDPG, BO, and random search together for 30 hours. And now let's look at the results. From the table, you can see that the human expert design achieves 6 GHz bandwidth with all hard constraints being satisfied, therefore receives the most innovative design award. But as you might have noticed from the table, random and BO method couldn't meet the noise hard constraints in the experiment, but DDPG meets all the hard constraints and achieves 5.78 GHz bandwidth, which is almost the same as the 6 GHz bandwidth from human design. The most fascinating things we can see here is that the DDPG method reaches an efficiency that is 25 times better than that of the human expert design, which is an amazing result we discovered from this experiment. Lastly, let's look at the curves of performance matrix and the versus the learning steps in the three-stage transimpedance amplifier. The vertical dashed line indicates the step when hard constraints are satisfied. As you may notice that in both four constraints matrix, they achieve that hard constraints at around 20,000 simulations. We can observe that power goes up and then goes down. Bandwidth goes up and then stays constant. Gain goes up and then remains. Therefore, from the RL agent's point of view, it firstly sacrifices power to increase hard constraints, for example, bandwidth and gain. After those two matrices are met, RL agents try to keep the bandwidth and gain constants and starts to optimize power, which is a soft optimization target. From this phenomenon, we can infer that RL agent has learned some strategies in analog circuit optimization by learning and rewarding. To conclude, this paper proposed learning to design circuit that leverages reinforcement learning to automatically optimize circuit parameters. The reason that we use reinforcement learning is that compared to supervised learning, it doesn't need large-scale training dataset, which is hard to obtain. How reinforcement learning works is that it iteratively getting observations, generating a new set of parameters by itself, getting a reward and adjusting the models step by step, and then finally get the correct prediction to the circuits that we want. Compared to the random search, Bayesian optimization, human experts LTDC can basically outperform all of those methods and reaches an efficiency of 250 times higher than what human beings can do. Under the same runtime constraints, L2DC can definitely do better than Bayesian optimization, which is the traditional way to design the circuits by learning. Thank you for watching.